Hello everyone. For today's video lecture we're going to be talking about impulse and momentum in particles. So far we've talked about using kinematics to relate position, velocity, and acceleration. We've talked about using the force, mass, and acceleration branch of kinetics to relate forces to accelerations. We've used the work and energy method to relate work and energy, a second branch of kinetics, as an alternative to the force, mass, and acceleration method. And then finally, we're going to bring in even a third branch of kinetics. The impulse and momentum method here is going to be an alternative to relate forces, velocities, accelerations, etc. All right, so the impulse and momentum method is based on, unsurprisingly, impulse and momentum. And so impulse and momentum are related in that the net impulse exerted on a body over some period of time will be equal to the change in that body's momentum. Equation-wise, this is what that looks like. So J is our impulse. And we're going to talk a little bit more about what an impulse is. And then mass times velocity is our momentum. So final momentum is going to be mass times final velocity. Initial momentum is mass times initial velocity. All right, so talking about impulse, the impulse of a constant force over a set time will be equal to the magnitude of that force times the duration of the time. So J, our impulse, is force times time. And so the force has a direction, it's a force vector, and so our impulse vector is going to have that same direction. We just need to multiply it by the quantity of time that we're using. All right, so more generally though, the impulse by any force, which the force may be changing over time, is going to be equal to the integral of the force over some set time period. So from time 1 to time 2, if I've got my force function, I take the integral, find the area under the curve, and that overall magnitude would be the area under the curve. Direction is just the direction of the force again. So that direction, we're only going to work with forces that have a constant direction. If you have a changing direction, we need to take that into account. It makes things a little bit more complicated. But for now, force has one direction, impulse has that same direction. All right, next up is momentum. And so the momentum of the body will be the mass of the body times the velocity of that body at any instant in time. So mass times velocity. And unlike impulse, which occurs over time, we need some set period of time for the impulse to occur, the momentum is instantaneous. So we need to find the instantaneous mass, instantaneous velocity. We're particularly going to be interested in some initial momentum and some final momentum. And a lot of things we deal with are collisions, so before collision, after collision, momentum is often quite important. So the impulse is going to be acting on the body between those 2 points in time. So I have initial, I have final, impulse happens in the middle. So momentum does have a direction, and it's simply the direction of the velocity at that instant in time. So they might not be the same. I might have a different final velocity and final initial velocity, and they have completely different directions. And that's all well and good. All right, so in 2 dimensions, remember that both of those things are vector quantities. So this is our vector equation. If we break that down into 2 dimensions, I can break it down into, say, x and y. The impulse in the x direction is the change in momentum in the x direction. The impulse in the y direction is going to be the change in momentum in the y direction. So break our forces down into x and y, break our velocities down into x and y, and then we have 2 scalar equations, whereas we had our 1 initial vector equation up here. All right, so how does all this come together? How do we solve a problem? Solving an impulse momentum problem involves 3 steps. So we've got some initial state, some final state, and the impulse is going to happen in the middle. So step 1 is we want to set up a diagram. We need to show the initial state, so initial velocity, initial mass, etc. And we want to identify any external forces that will be acting on the body between the 2 states, and identify the velocities known or unknown in each state. So we've got initial diagram, final diagram, impulse is going to happen in the middle. All right, so we're going to use the diagram to put together the impulse momentum equation, or equations if we break it down to x and y, with the included known and unknown values. So our base equation, impulse is equal to final momentum minus initial momentum. We break that into x and y, put in any known, say we know all of the initial velocities, we know the impulse, we'd be solving for the final velocity. And that's the last step. So step 3 is once we have our impulse momentum equation or equations set up, we simply need to solve for the unknown variables. And in this case, if we have a two-dimensional problem, we're going to have two equations. We could solve for up to two unknowns. It could be a final velocity in x and y. It could be a time for the impulse. It could be the magnitude of the force. It could be a lot of different quantities in all this. But the important thing is we're usually going to have two equations, so we can solve for up to two unknowns. And with that, that's all I've got for today's video lecture. Thank you for watching, and I hope to see you again.